How's it going, everyone? So in this video, we're going to continue on with our examples of related rates by going over 2 or 3 examples. So let's begin here. Example 6 tells us that we have a boatyard's total profit from selling X outboard motors is given by P equals to negative X squared plus 100X minus 2,000. Now, if the outboards are selling at a rate of 20 per week, well, how fast is the profit changing when 400 motors have been sold? Okay, so as you can see, this problem doesn't require us to use a diagram, so let's just go ahead and jump straight into identifying the rates. So what are the rates that we see in this problem? Well, let's see, we have here that the outboards are selling at a rate of 20 per week. Okay, so I'm going to say here that since our X was equals to the outboards, or the outboard motors, then the dx/dt, the rate at which the motors are selling here, is 20 per week. Put here 20 motors per week. Okay, now we want to figure out how fast is the profit changing when 400 motors have been sold. So we want to see, okay, well, if it's how fast the profit is changing, well, that is mentioning there the rate of change of the profit. The thing is, though, we don't know this one yet. Not to worry, though. We'll figure it out. Okay. So let's go ahead and see if we can come up with an equation that relates the outboard motors to the profit. But lucky for us, there is no need to do that because we already have the equation right here. We're being told, well, let me write down here equation. And the equation that relates all of that is going to be the P equals to negative X squared plus 1,000X minus 2,000. Okay. So let's go ahead and take the derivative here. Again, it's always with respect to time. So the derivative with respect to time of the profit here is going to be equals to negative, well, keep it here. The derivative with respect to time of the negative X squared plus the derivative with respect to time of the 1,000X minus the derivative with respect to time of 2,000. Okay, so what does this give us here? Well, we're going to have dp dt equals to a negative 2x times dx dt plus 1,000 times the derivative of x with respect to time, so times dx dt, minus, well, the derivative of 2,000 is 0, so it stays like this. Okay. So this is our equation now, so we're ready to substitute. So let's go ahead and substitute here. Now with the substitution, we gotta be careful because we're substituting at a specific moment. And yeah, we're looking specifically when X is 400. So when X, the number of motors sold, are 400, what's going to be the rate of change for the profit? Well, let's see. We have here dp dt is equals to a negative 2 times X times dx dt, which we knew was 20 motors per week, plus 1,000 times dx dt, which was the 20. Okay. Now, what will that give us here? Well, if we plug everything into the calculator, I get a 4,000. Okay. Now, what are my units here? Well, the profit is going to be increasing at 4,000. Let's see. Well, I guess there were no units for the profit here. I guess it would have been dollars per week. Okay. So if you're selling boats or outboard motors, I'm sorry, at a rate of 20 per week, then your profit is changing here at a rate of $4,000 per week. Okay. This one here, as you can see, it wasn't too bad because, well, there was no need to make a diagram and we were pretty much given the equation. We just had to be comfortable using implicit differentiation with respect to time. Okay. Now, let's take a look at another example here. Okay, so this is a good one here. It's a little bit different. So this one here is telling us that water is running at a conical funnel at a rate of 1 inch cubed per second. Now, if the radius of the base of the funnel is 4 inches and the height is 8 inches, we want to find the rate at which the water level is dropping when it is 2 inches away from the top. Now, here's a hint. The formula for the volume of a cone is 1/3 pi r squared h, where r is the radius of the base and h is the height. Okay, so let's see. What is it that we have here? Well, we have water running out of a conical funnel at a rate of 1 inch cubed per second. Now, since we have a conical funnel, that's what I'm going to be including in my diagram. Okay, so let's see. I'm going to have the top of the funnel here. There you go, something like this. And let's make the conical funnel. There we go. Something like this, and there we go. It is dripping here. And the way or the rate at which it is dropping water or the water is funneling out, it is 1 inch cubed per second. So remember, this is a changing volume here because it's inches cubed per second. So I'll put this one here as dV dt equals to negative 1 inch cubed per second. And again, notice I have it negative because the volume itself is decreasing because you are losing water. Okay, what else do we know here? Now we have that the radius of the base of the funnel is 4 inches. So, okay. This one here is going to be 4 inches. Now the height is 8 inches. So put here the height is 8 inches. Okay, good. Now we want to figure out at what rate is the water level dropping when it is 2 inches away from the top. So I'm going to go ahead and draw the water level here. And this one here, it is dropping. Now we want to figure out how much it is dropping. So notice here that the height of the water here is changing. So basically we want to figure out, oh, well, okay, well, how is the height of the water changing? Okay, so here is our diagram. I'm just going to move this a little bit more to the side. There we go. So we can clearly see the inches cubed here. Alrighty. Now, let's identify the rates that we have and the rates that we don't have. Now for this one here, the rates, well, we saw that the volume was decreasing at a rate of negative 1 inch cubed per second. Now, what else do we know? Well, we don't know the rate at which the height of the water is changing. And that seems pretty much what we want to find out. But I also have some other quantities, right? We are also talking about the radius here. So I'll put here, what about the radius? How is the radius changing? Okay. Now, let's come up with the equation, which was given here. the equation relating the volume, the height, and the radius of a right cone here is volume equals to 1/3 pi r squared times the height. Now, at this point, normally we would have been taking derivatives, but this problem is different from the other ones that we tried so far, because notice we have a volume, a radius, and a height. So if I took the derivative right now, technically, since both the r and the h are functions of time, when you took the derivative with respect to time, you would need the product rule. Which in itself is not really a problem, but the problem that will come from this though is, as you take the product rule, you would end up with a dr dt. But we have no idea what the dr dt is. We know that we have to find a dHdt, but I don't have enough information to figure out the dr dt. So, at this stage, we're going to be performing a trick in order to avoid the dr dt. Now, what is that trick? Well, we're going to use similar triangles. So let's see here, use similar triangles. Now, what was it about similar triangles here? Well, remember, if we have essentially two triangles, I'm going to split down this cone here down the middle. So if I split this cone around the middle, then we have the following scenario. We have the big cone right here, whose height was 8 inches, and its radius was 4 inches. Now, I'm going to draw the water level right here. So if I draw the water level, well, notice you're forming now another triangle within the big triangle. So now we have this smaller triangle. Now, this smaller triangle is going to have its own height and its own radius. Now, I'll call this one here, this height, I'll keep it here with a light blue. Actually, let me give myself a little bit of room. There we go. Okay, I'm going to have this height right here and this smaller radius right here. Now, a very nice thing about similar triangles is that basically they have the same ratios, or the ratios of their sides. So for example, the ratio between the big triangle, which is, or the ratios of the radius of the big triangle to the height is 4/8. But because you have similar triangles, this ratio must be the same as the one for the smaller triangle. So it should be equals to r/h. Now, setting up this ratio here allows us to do the following. I'm going to go ahead and solve for r. In fact, I'm going to just kind of move it here to the side. Now, if I go ahead and solve for r, then I'm going to have r equals to, well, we multiplied by an h here, multiplied by an h here. And that's going to give us, let's see, 4/8 is 1/2. So it's going to give us a 1/2 times h. And that's after canceling this one here. Okay. Now, we have that r is equals to 1/2 the height. Now, why is that so useful? Well, now that we know what the r is, we can go ahead and plug it in directly into our volume equation. So our new equation is the following. We'll have the volume is equals to 1/3 pi times the radius, which we now know is 1/2 times h, squared times h. So what will that give us then? Well, let's see. That's equals to 1/3 pi times 1/4 h squared times h, which gives us the formula. The volume is equals to pi times h cubed over 12. Now, this volume equation, it's looking a lot simpler than the one that we started off with. And the beauty of it is that now we see that the volume only depends on the height of the cone, not the radius. So, with that said here, now we can find the derivatives. So I'll put here differentiate. Okay, so taking the derivative with respect to time here. So the derivative with respect to time of the volume is equals to the derivative with respect to time of the pi over 12 times h cubed, which is going to give us the following. dv dt is equals to pi over 12 times, okay, now what is that derivative of h cubed? That's going to be a 3h squared, but because it's implicit differentiation, I'll also have here the dh dt. Okay, now this is the equation that we're going to be working with. Now we can go ahead and substitute. Okay, so what is that we know? Well, we knew that the dv dt was -1 inch cubed per second. So we're going to have here a -1 equals to, well, can we simplify the pi over 12 times 3? I think we can. 3 divided by 12 is 1/4. So we're going to have here pi over 4 times the height. Well, what was the height? Let's see. We're being told that we're interested in when the top is, or when the water is 2 inches from the top. Okay, so if the water here is 2 inches from the top, then what's the height that we're focusing on? Well, if the water is 2 inches from the top, then that means that basically we're focusing when the height, or we're focusing at a height of 6 inches, right? Because if the whole funnel was 8 inches, but then the water level is starting, or we're focusing when the water level is 2 inches away from the top, then you're focusing when you're trying to find out, okay, what's the rate of change as the height is 6 inches. So I'll put it here when h is equals to 6. Okay, so substituting things in, on the right hand side we have a pi over 4 times the height squared, so times 6 squared, times dh dt. Okay, so let's go ahead and simplify that to see what we get. So this is going to give us a -1 equals to pi times 36 divided by 4 times dh dt. Now 36 divided by 4, that's equals to 9. So if we want to get the dh dt by itself, we're going to go ahead and divide both sides by 9 pi. So divide here by a 9 pi, divide here by a 9 pi, and it looks like the height is changing at a rate of -1 over 9 pi inches per second. So this one here was a little bit tricky because of the substitution using similar triangles. But once we've substituted, I would say that the derivative was actually easier. So let me know what you guys think on Wednesday so we can go over maybe more problems. Okay. Okay, so let's take a look at one more problem that's similar to the one that we just tried. Alright, so for example 8 here, we have a street light that is atop of an 11-foot tall pole. Now a woman 6 feet tall walks away from the pole with a speed of 8 feet per second along a straight path. Now we want to know how fast is the tip of her shadow moving when she's 35 feet away from the base of the pole. Alright, so let's go ahead and reread the problem and see if we can come up with a diagram. So let's see here. Let's go with the diagram. Okay, so what's going on here? So we have a street light that is atop of an 11-foot tall pole. So put here a pole here. This one here is 11 feet tall. Then what else do we have here? We have a woman that is 6 feet tall walking away from the pole. So put the woman right here. Okay. She's walking away from the pole casually. And she is 6 feet tall. So put here 6 feet tall. Okay. Now we know that she is walking away from the pole at a rate of 8 feet per second. So okay, she's going there at a rate of 8 feet per second. I'll put it here. She's going at a rate of 8 feet per second. Okay. Now, we want to know how fast is the tip of her shadow moving when she's 35 feet away from the base of the pole. So let's see. In fact, I think I'm going to move. There you go, some animation there. Now that's only because I want to be able to see the shadow a little bit more clearly. So here's a pole, light here. So we see the light coming. So she is casting a shadow. And right over here, we have the tip of the shadow. Okay. So this is what's happening in our problem here. Now, how can we do it? How can we solve it? Well, what I want you guys to notice right now here is that, okay, yeah, it looks like we are dealing with triangles. But more specifically, though, it looks like we have a triangle inside of a triangle. Very similar to the one that we just did above. So it looks like we can use similar triangles to help us solve this problem. Okay, now how do we solve it though? Well, notice that the distances that we're referencing here, they all have to do with the base of the pole. So we're being told, yeah, we're a given distance away from the pole. So what I'm going to be doing here is I'm going to define two variables. I'm going to define the variable L to be the distance of the tip of the shadow from the base of the pole. I'll just put here distance of tip of the shadow from pole. Okay, so we have this full distance here to be a distance of L. Okay. Now, because we're looking for how fast is the tip of the shadow moving when the woman is 35 feet away from the pole, I'll let X be the distance of woman from the pole. Okay, so I have an X right here. Okay, now this is what's going to allow us to create the triangles. So I'm going to go ahead and use an equation with similar triangles. Okay. All right. So if we're going to be using similar triangles, remember, it's all about the ratio. So the first ratio here is, well, the ratio of 11, the height of the big triangle, to the base of the triangle, so 11 to L, this should be the ratio of the smaller triangle. Now the height of the smaller triangle here is 6 feet. That's the height of the woman. Put it here. So it's 6 feet. But what about the base of that triangle though? Well, if we know that the whole distance here was L, and then this part is X, then the base of the smaller triangle should be the full length minus X. There we go. And again, this is very similar if I said that, oh, I have a piece of wire that its total length is 10 inches, but then I cut something here 2 inches, then what's left over? Well, this one will now be 10 minus 2. And that's exactly what we're doing here. Okay. So, using similar triangles, our ratios are now 11 to L equals, or 11 is to L just as 6 is to L minus X. Okay. Now, based on the variables that we just labeled, the rate at which the rate at which the woman was moving along is now our dx dt. Okay. All right. There we go. We have identified the rates, and we know that we want to find out what is the dl dt. How is the tip of the shadow, or how fast is the tip of the shadow moving when the woman is moving at 8 feet per second? So let's go ahead and simplify our equation a little bit, because we want to find out what is the LDT. So I'm going to solve for L here. I'm going to cross multiply. This multiplies this multiplies this, and this is going to give us 11L minus 11X is equals to 6L. Alright, so I'm going to go ahead and subtract the 6L, subtract the 6L. So that's 5L. I'm going to go ahead and add an 11X, add 11X. So we have 5L is equals to 11X. Alright, so now we can go ahead and divide by 5. Divide by 5. So it looks like L is equals to 11/5 X. And there we go. We have our equation right here. Now notice this one. It's a very simple equation. Now all that we need to do here is differentiate. And let's see, we're differentiating with respect to time. Have here the derivative. The derivative with respect to time of L is equals to the derivative with respect to time of 11 over 5 times X. So this is going to give us here a dl dt, which is what we're looking for. And that's equals to 11/5 is a constant. It comes along for the ride. Now what is the derivative of x with respect to time? Well, that is just a dx dt. And there we go. Now all that we need to do is substitute. But notice for this one though, even though we were looking specifically how fast was the tip of the shadow moving when she was 35 feet away from the base, if you take a look here at your equation, your dl dt, it doesn't even take into account the x. All it cares about is the rate at which the woman was moving, which was 8. So our answer should be dl dt is equals to 11/5 times 8, which if we plug into a calculator, that should give us here, let's see, I believe in 17.6 feet per second. So that's how fast the shadow is moving as a woman moves 8 feet per second. But here 17.6 feet per second. So as you can see, this problem here was a little bit different. It didn't require us to use any complicated formulas. It was simply coming up with a ratio. Nonetheless, I mean, coming up with a ratio is not necessarily easy, because we had to come up with a variable here, L, to represent the length from the base of the pole all the way to the tip of the shadow. And that's what we wanted to see how it was changing. Now, we did use similar triangles, but we had to take into account the fact that the distance from the woman to the pole was L, so that meant that the base of the smaller triangle was L minus X, and that was the key. Okay, so with that said, this is going to be the end of the examples for related rates. Hopefully, if you take a look at those in the homework, and they're not too bad. Alrighty, have a good one.